Okay. So, let us continue the discussion on Ramjet. So, we are in the middle of the discussion of the Ramjet cycle analysis, and we have looked at both the ideal cycle and the actual cycle. So, there are a couple of more things that I would like to discuss, and then we will look at the Scramjet analysis. So, one of the thing that becomes is that also there is an application which is called nuclear Ramjet. Okay. So, this is like the principle behind this nuclear Ramjet is bit relatively simple. So, there are the three basic components are the same, but the nuclear Ramjet is used to heat the air of burning fuel in a combustion chamber. So, some additional components are used compared to Ramjet. Okay. And also like some Ramjet components plus some additional component like reactor core plus radiation shield and heat exchanger. So, these are the some of the other extra component which are kind of used. Okay. And so, one can have a like an schematic like how it can look like, that you have a sort of an a moderator here, and then the moderator from here it sort of goes back, and then like you have this nuclear reactor. This is the nuclear reactor, and then it goes to like from here the things start, and you have some piping here, and this will be sort of enclosed, and this is where this is what you have the air inlet. This is where the nuclear heat goes in, and this portion is essentially your Ramjet portion, and this is your exhaust or exhaust. So, this connection kind of connected with the pump and comes back. So, this is just a schematic how it looks like, but we will not go very much details of that. What we will be more interested to another important one, which is called the double throat Ramjet engine. So, double throat Ramjet engine, we will look at the schematic. So, this is double throat Ramjet. Now, just and it will look like this. So, this will go, then maybe this will go up, then second throat, and then goes like this. And if we just have a basement here, then this is the spike, so that takes into account, and then kind of exiting out. So, you can have sort of different like cross shock interaction, then so from this portion up to this is intake, and then this is the portion which is combustion chamber. So we can have the burners here. Let us say 1, 2, 3, and then this portion is nozzle. So that is 4. So it has 2 throats. The first one is to decelerate the flow to subsonic before combustion chamber, and second one is to accelerate the flow to again supersonic. So this guy supposed to decelerate before it comes to the combustion chamber, and this throat is supposed to accelerate, so that you get. So DTR, this double throat ramjet, it has a supersonic subsonic intake followed by a subsonic combustion chamber, then a subsonic supersonic nozzle. So the flow is decelerated, supersonic flow. So it enters combustion chamber, then again it actually the exhaust it actually again increases to a supersonic flow. And the typical TS diagram that one can have is that you go to 1, then 1 to 3, 3 to 4. So this is 1, this is 0 2, then 0 3, so that is T naught 3, this is T naught 2, then T 4, T 1. So that is how the diagram would look like. Now that is a double throat ramjet. Now then we will move to the scramjet. So it is a called the supersonic combustion ramjet. That is what the name stands for. So experimental scramjet powered is that Boeing X-51A. The test craft was lifted to flight altitude by a Boeing B-52 Stratofortress before being released and accelerated by a detachable rocket to near Mach 5.1. So this was tested in 2013. So it also has 3 basic components like intake, combustor chamber, nozzle. While this is also conceptually very simple, but actual implementation is very limited, and because of the technological challenges. Now only limited testing can be performed in ground facilities. Long duration full scale testing requires flight test speed above Mach 6. Now also the hypersonic flight within the atmosphere generates immense drag temperatures found on the aircraft within that engine, and then also maintaining combustion in supersonic, as the fuel must be injected, mixed and ignited. So that is a challenge. So within few milliseconds. So these are the some of the challenges. That there are 2 families of operational application can be seen for this high speed propulsion. One is let us say combined air breathing or rocket propulsion for space launcher, and second one could be the military system, mainly missiles and drone, like that. And the evaluation, so first in 1940 in the R&D started in USA and Canada. So then later on there are different development which took place, and the latest one is that now there are different countries which are involved at present now, like hypersonic programming, Germany, India, Brazil, they are also all are in this these things. So advantage and disadvantage of this scramjet. So if we put some advantage and at the same time some disadvantage, like one of the biggest thing that it does not need to carry oxygen. Second, no rotating parts, which makes it easier to manufacture. A high specific impulse, so that is another beauty of that. Fourth, higher speed could mean cheaper access to outer space in future. Then disadvantages, it cannot produce efficient thrust unless boosted to high speed, let us say around Mach 5. For a horizontal takeoff, scramjet would need neither a rocket or a combined propulsion system like turbojet or turbofan to boost it to some Mach 2 to 3, followed by another propulsion method like ramjet or rockets. So that is a problem. Then testing is expensive. So any prototype design also are extremely expensive, hypersonic test chamber or large vehicle, because not only high instrumentation cost, also other factors which are involved. Lack of stealth, as the vehicle would be very hot due to high speed within the atmosphere, and it would be easy to be detected with infrared sensor. The increased cooling requirement, so increased cooling requirement of scramjet engines result in lower efficiency. So these are some of these things. So now we can draw a schematic of the engine, let us say like this. And we could So, this portion is the sort of intake, then this is combustion chamber and this is nozzle. So, 1, 2, 3, 4, here you will have all this shock, like this, and if I put the TS diagram, so this 1 to 2, three, so that is 4, 1, 2, okay, T4, T1, T2, T3. So, this is combustion chamber, this is intake, this is nozzle. Okay, let us say this point is somewhere y, this point is x. So, station 1, it's the represent the intake, inlet of the intake, which is also beginning of the compression process. Since the hypersonic shock wave angles are small, the ramp or spikes are long, and so then station 2, it starts the combustion entrance of the combustion chamber, and it's in a fixed geometry scramjet. The pressure at the combustion chamber varies. 3, it's the exit of the combustion chamber and entry to the nozzle, and the station 4, it exit of the nozzle. Now, we look at the intake first, and intake module. So, what will happen, because of the shock there are losses. So, intake isentropic efficiency would be T x minus T 1 by T 2 minus T 1. So, the area ratio would be m 1 by m 2, 1 plus 0.5 into gamma c minus 1 m 1 square, 0.5 into gamma c minus 1 m 2 square by gamma c plus 1 by 2 gamma c minus 1. Similarly, we will get T 2 1 plus 0.5 into gamma c minus 1 m 1 square, 1 plus 0.5 into gamma c minus 1 m 2 square, and P 2 by, so P 2 by P 1 or P 2 equals to P 1 1 plus eta I T 2 by T 1 minus 1 gamma c by gamma c minus 1. So, the inlet total pressure recovery is modeled with MIL. So, it is modeled with MIL spec E 5007D, which can provide some correlations. These correlations are like P naught 2 by P naught 1 is 1 for M 1 less than 1 and 0, P naught 2 by P naught 1 is 1 minus 0.0776, M 1 minus 1, and this is the range where 1 to 5, and P naught 2 by P naught 1, it would be 800 by M 1 to the power 4 935, which is M 1 greater than 5. So, then we go to the burner, and once we go to the burner, then we again do the analysis. So, what we get, T naught 3 equals to m dot eta b QHB by CPH m dot A plus F m dot A CPC T2 by CPH m dot A plus m dot F 1 plus 0.5 into gamma c minus 1 m2 square. So, T naught 3 by T naught 2 would be m3 square by m2 square 1 plus gamma c m2 square m3 square 1 plus 0.5 into gamma h minus 1 m3 square by 0.5 into gamma c minus 1, and P3 equals to P2 1 plus gamma c plus 1 gamma c m3 square, and T3 equals to T naught 3 by and similarly nozzle, we will get the nozzle. So, eta n is T3 minus T4 by T3 minus Ty. So, T4 is T3 minus T3 eta n 1 minus P2 by P3 gamma h minus 1 by gamma h, and V4 is 2 CPH T naught 3 minus T4. So, if we put the block diagram, it looks like we have a block diagram here. This is intake. So, you have M1, T1, P1, this is where M2, then combustion chamber, this is A2 by A1, from here it goes T2, P2, M dot A, M dot F, then we get to nozzle where M3, P3, T3, and then finally T4, V4, and this goes here. So, now we just look at the performance analysis, and when you do that, so the thrust would be m dot A plus m dot F V4 minus m dot A V1. So, T by m dot A would be 1 plus F V4 minus V1. So, TSFC would be m dot F by T, T by m dot A, and then propulsive efficiency, which is T into V1 by delta kinetic energy. So, that means it could be written as to V1 m dot A plus m dot F V4 minus m dot A V1, then m dot A 1 plus F V4s minus V1 square. So, this is what we can write is 2 V1 into V4 1 plus F minus 2 V1 square divided by 1 plus F V4 square minus V1 square. So, if F is small, then eta PR, this propulsive efficiency is 2 V1 by V1 plus V4, and similarly we can find out thermal efficiency. It is delta kinetic energy by Q added. So, this would be m dot A 1 plus F V4 square minus by 2 m dot F eta combustion chamber QHV. So, which is written as minus V1 square divided by 2 F QHV eta Cc. So, again if small, this will boils down to like V4 square minus V1 square by 2 F eta Cc QHV, and overall efficiency which would be eta PR into eta thermal efficiency, and ISP would be T by m dot G. So, these are all the performance parameter that one can calculate and look at. So, there could be another one which could be looked at is that, so which is called dual ramjet. So, this is dual ramjet is also a dual mode scramjet. So, where the ramjet at low speed, where ramjet at low speed and transform to scramjet at high speeds. Okay. So, that is why it is called dual mode. So, now I mean basically this is another advancement where one can also look at these things and can do the thermodynamical analysis that. So, this will also have a similar component like intake or inlet. Then I mean it will have, let us say, component like intake, then there would be isolator, then there is combustion chamber, then there would be nozzle. So, these are the some of the component. Is just like if somebody draw a schematic like that, and if that is the spike, so these are the pattern of the shock. So, now this portion is essentially, this is the intake, then there would be this portion which is called the isolator, then this portion which is combustion chamber, and this is nozzle. And also I mean if you draw the TS diagram, then you can always do this aerothermodynamic analysis. So, that's can be also done. So, essentially these are also some of the advancement in the scramjet application that where people can use all this, but eventually it is important to note that these scramjet things are still at the experimental mode. I mean none of the flight, I mean only the flight which was given some test by US, but others, all other countries, they are in this scramjet hypersonic program. They have different program in hypersonic zone where they are about to build some prototype and then basically demonstrate the technology. So, mostly I would say these are all at the level of technology demonstration. So, that is what different countries what they have this program, these different vehicles they are into or the kind of things they are trying to develop. These are called technology demonstrator vehicle, hypersonic technology demonstrator vehicle, and they have pretty much the I mean outer configuration or the from apparently they look probably similar, but because they built on the same principle, similar kind of things, but this is really a challenge. So, we will close the discussion on Scramjet here, or rather stop the discussion on Scramjet here, and we will move to the next set of engine for discussion in the next class.